1942, Philadelphia, Pennsylvania. The technical review from American railroad engineers would condemn what the War Department was proposing in a hastily converted Baldwin Locomotive Works production facility, a mass-produced steam locomotive designed using methods that contradicted everything American railroading had perfected over decades of refinement and competition. Through the clang of welding torches and the glow of assembly lines running triple shifts, Army Transportation Corps engineers sketched designs with utilitarian simplicity that railroad master mechanics dismissed as crude emergency measures. No precision castings, no refined appliances, no reliance on the specialized components that American locomotive builders had perfected through generations of competitive innovation. In American railroad shops, locomotive construction achieved excellence through hand-fitted components and precision machining that created engines reflecting decades of engineering evolution. Each locomotive carried the distinctive characteristics of its builder's philosophy, whether Baldwin's massive driving wheels, Lima's superheater arrangements, or American Locomotive Company's balanced valve gear designs. Most operated with reliability that demanded specialized maintenance crews and premium fuel. The Army was proceeding with an industrial philosophy that railroads declared fundamentally inadequate. Welded boilers instead of riveted construction, simplified valve gear, crude standardization that eliminated the refinements American railroading considered essential for efficient operation. 8,000 miles from European war zones, the most controversial locomotive design in American history was taking shape in Baldwin's production facilities, not through decades of competitive refinement, but through military urgency that would prove industrial expediency could achieve what peacetime engineering never imagined necessary. The locomotive components scattered across the Pennsylvania Railroad's testing facility told a story of European engineering refinement that American military planners had accepted as the standard they must somehow match. Each precision-machined piece came from a captured German locomotive that had operated flawlessly across European networks for 2 decades before Allied forces seized it in North Africa. Railroad inspectors examined the German craftsmanship with professional admiration, noting the precision tolerances visible in every bearing surface and valve component. The Europeans had achieved operational efficiency that American military logistics insisted was impossible with wartime manufacturing constraints. European locomotives dominated international railroading through engineering sophistication that no hastily designed American alternative could match. Built in specialized shops that traced their techniques back to the earliest days of railway development, these machines carried the weight of engineering tradition alongside. Their mechanical loads, master craftsmen in Germany, Britain, and France maintained construction standards passed down through generations of apprenticeships, creating locomotives that commanded respect across international railway systems. Each component underwent individual attention from specialists who could judge proper fitting by measurement, precision, and surface finish, adjusting assembly based on tolerances that reflected decades of accumulated engineering knowledge. Yet for all their sophistication, American military planners understood that European construction methods would never meet the urgent demands of global warfare. The smooth rail networks of peacetime Europe had never prepared locomotive designers for the punishment of bombed-out tracks, makeshift repairs, and relentless operational demands that modern warfare would impose on railway equipment. American locomotive builders had spent decades pursuing efficiency through complexity, creating machines that represented the pinnacle of steam technology refinement. The Pennsylvania Railroad's K4 Pacific locomotives featured precisely balanced valve gear, sophisticated superheating systems, and roller-bearing assemblies that required specialized maintenance but delivered unmatched performance on well-maintained tracks. Baldwin Locomotive Works took pride in construction standards that emphasized precision machining and careful component matching. Their production facilities housed specialized equipment for grinding bearing surfaces to tolerances measured in thousandths of an inch, while assembly procedures demanded skilled workers who understood the subtle adjustments that optimized locomotive performance. Each American locomotive represented months of careful construction involving hundreds of precision-machined components. Boilers received riveted construction that required master craftsmen to create leak-proof seams through hammerwork that compressed metal without cracking. Valve gear assemblies demanded precise timing adjustments that balanced steam distribution across cylinders within fractions of a degree. The sophisticated engineering created locomotives capable of extraordinary performance under ideal conditions, pulling passenger trains at sustained speeds exceeding 100 miles per hour while maintaining remarkable fuel efficiency. Railroad companies invested in specialized maintenance facilities staffed with expert mechanics who understood the intricate systems required to keep these complex machines operating at peak performance. European designs followed similar philosophical approaches, emphasizing refined engineering that achieved efficiency through precision rather than brute force. British locomotive builders developed compound expansion systems that extracted maximum energy from steam through multiple cylinder stages, while German manufacturers perfected streamlined boiler designs that minimized heat loss during operation. The problem confronting American militaries, in short, planners extended beyond merely designing a locomotive. European railway systems operated with infrastructure support that wouldn't exist in war zones. Maintenance facilities equipped with precision tools, reliable fuel supplies of consistent quality, and tracks maintained to exacting standards that prevented excessive wear on sophisticated running gear. Military operations demanded locomotives that could operate under conditions no peacetime railroad would tolerate. Bomb tracks with temporary repairs creating sudden grade changes and alignment shifts, fuel of questionable quality contaminated with debris, maintenance performed by soldiers with minimal training using whatever tools remained available after combat operations. The Army Transportation Corps calculated that European locomotive sophistication, even if successfully replicated under wartime production constraints, would prove catastrophically unreliable when subjected to combat zone conditions. Complex valve gear would fail when track irregularities created frame stresses that precision mechanisms couldn't tolerate. Specialized bearings would seize when maintenance intervals stretched from weeks to months. Riveted boiler construction would develop leaks when rough track subjected seams to stresses they were never designed to withstand. Colonel Howard Hill, directing the Transportation Corps Locomotive Development Program, understood that military operations required abandoning peacetime engineering philosophy entirely. The locomotive that would win the war wouldn't be the most efficient or sophisticated machine American industry could build. It would be the crudest, simplest design that could survive conditions that would destroy conventional locomotives within weeks of deployment. The specifications Colonel Hill presented to Baldwin Locomotive Works in January 1942 read like a deliberate rejection of everything American locomotive engineering had achieved. Welded boiler construction instead of traditional riveting, eliminating the skilled craftsmen and time-consuming hammer work that riveted assembly required. Simple two-cylinder design without the sophisticated compound expansion systems that European railways considered essential for fuel efficiency. Baker valve gear, chosen not for optimal performance but for its simple design using the fewest possible components. No roller bearings, no specialized appliances, no refinements that required precision manufacturing or skilled maintenance. The locomotive would use plain bronze bearings that any machinist could fabricate, standard fittings available from multiple suppliers, and components designed for replacement rather than careful adjustment. Baldwin's engineers protested that the specifications violated fundamental principles of efficient locomotive design. Welded boiler construction had never been proven reliable for high-pressure steam service, with metallurgists warning that weld integrity would fail under thermal cycling that riveted construction handled through slight flexibility in the seam design. The simplified valve gear would waste steam through inefficient distribution that precision timing mechanisms prevented in conventional designs. Plain bearings would generate excessive friction compared to roller bearing assemblies, increasing fuel consumption while requiring frequent replacement due to wear that sophisticated bearing designs minimized. Colonel Hill dismissed every objection with single response. The locomotive must be buildable by facilities with minimal specialized equipment, maintainable by personnel with basic mechanical training, and repairable using whatever materials remained available after supply lines were disrupted by combat operations. Performance efficiency mattered far less than operational survival under impossible conditions. The design that emerged represented industrial expediency in its purest form. The boiler used arc welding throughout, with seams that skilled welders could complete in hours compared to days required for riveted construction. The barrel measured just 60 inches in diameter, small enough that standard steel plate could form it without requiring specialized rolling equipment. 2 cylinders drove 5 coupled driving wheels through connecting rods machined from standard bar stock rather than precision forgings. The Baker valve gear used simple pins and links that any blacksmith could fabricate if combat damage required field repairs. The entire locomotive weighed 62 tons, light enough for temporary bridges while carrying enough coal and water for reasonable operating range. Army engineers designated the design S160, simply indicating a steam locomotive with 160,000 pounds tractive effort, the pulling power calculated from cylinder dimensions and driving wheel diameter. No elaborate classification system, no builder's pride in distinctive design features, just utilitarian identification for a machine built to accomplish one mission: move military supplies across war-torn railways until it fell apart, then be replaced by an identical unit rolling off production lines running around the clock. Baldwin workers accustomed to careful construction found themselves assembling locomotives using methods that violated every standard they had learned. Welders joined boiler plates with continuous seams rather than carefully spaced rivets, creating joints that inspection procedures couldn't verify with traditional confidence. Components bolted together with standard hardware instead of custom-fitted assemblies that required hours of careful adjustment. The first completed S160 locomotive emerged from Baldwin's facility in September 1942, looking crude compared to the refined machines that normally left the works. Exposed welding beads marked every boiler seam, rough castings showed minimal finish machining, and the entire assembly carried an industrial appearance that suggested temporary expediency rather than permanent railway. Equipment. The initial deployment of S160 locomotives to North African railways in early 1943 confirmed every concern that American railroad engineers had expressed. Operating crews reported rough riding that resulted from simplified suspension, excessive coal consumption from inefficient valve gear, and maintenance demands that seemed to prove the design fundamentally inadequate for sustained operations. Military railway service battalions struggled with unfamiliar equipment that lacked the refinements American railroaders expected. The locomotives pulled poorly compared to the captured European engines they replaced, consumed fuel at rates that strained supply logistics, and required constant attention to bearings that wore rapidly under North African dust and heat. Reports reaching the Transportation Corps suggested the S160 program might represent expensive failure that wasted resources on inadequate equipment. Railroad officers recommended canceling further production in favor of acquiring proven European designs through lend-lease agreements with British locomotive manufacturers whose products had demonstrated reliability under wartime conditions. The transformation began not through engineering improvements, but through operational necessity that revealed unexpected strengths in the crude design. As Allied forces advanced into Sicily and southern Italy during mid-1943, railway conditions deteriorated beyond anything peacetime railroading had imagined possible. German demolition teams had systematically destroyed every significant railway structure, dropping bridges into rivers and cratering tracks with explosives that left rails twisted into unusable wreckage. Allied engineers rebuilt lines using whatever materials remained available, creating temporary bridges with weight restrictions that prohibited conventional locomotives, while installing track with alignments that curved sharply around damaged sections. The sophisticated European locomotives that had operated flawlessly on peacetime railways failed catastrophically under these conditions. Precision valve gear jammed when rough track created frame distortions that disrupted careful timing adjustments. Riveted boilers developed leaks as temporary track subjected seams to stresses they were never designed to handle. Roller bearing assemblies seized when maintenance, intervals stretched from scheduled servicing to occasional attention whenever combat operations permitted. S160 locomotives kept running. The welded boiler construction that railroad experts had declared unreliable proved remarkably tolerant of stress that would fracture riveted seams. Continuous weld penetration distributed loads across entire joints rather than concentrating stress at discrete rivet points, allowing the boiler to flex slightly under extreme conditions without developing leaks. The simple Baker valve gear that wasted steam through inefficient distribution couldn't jam because it had no precision timing. Mechanisms to fail. plain bronze bearings wore quickly but could be replaced by any machinist with basic lathe skills, while the crude design tolerated dust and debris that would destroy sophisticated bearing assemblies within hours of exposure. Military railway service crews discovered that S160 locomotives could operate on tracks that European engines refused to traverse. The lightweight cross-temporary bridges rated inadequate for heavier power, while short wheelbase negotiated curves that longer locomotives couldn't navigate without derailing. The crude suspension that rode roughly on good track absorbed punishment from rough roadbed without transmitting destructive forces to the frame. By late 1944, S160 locomotives were operating across every theater where Allied forces maintained railway operations. The 2,120 units produced had become the backbone of military logistics in Europe, North Africa, and Asia, hauling ammunition, supplies, and troops across railway systems that existed in various states of destruction and temporary repair. What American railroads had dismissed as crude emergency equipment had proven more reliable under extreme conditions than any locomotive design ever created. The paradox confronted peacetime engineering assumptions with uncomfortable truth. The sophisticated refinements that optimized performance under ideal conditions became catastrophic vulnerabilities when conditions deteriorated below perfect maintenance and infrastructure support. European railway administrators watching S160 operations recognized capabilities their refined locomotives couldn't match. French railway engineers observed American locomotives operating across hastily repaired lines where their own sophisticated compounds sat disabled by mechanical failures that rough trackage had induced. British railway officers noted S160 units pulling loads through mountain passes where their carefully maintained express engines had failed due to fuel quality variations. The technical reports reaching railroad companies worldwide documented operational realities that challenged fundamental engineering philosophy. S160 locomotives consumed 20% more fuel than efficient European designs, but they ran continuously while sophisticated engines sat awaiting parts and skilled maintenance that combat conditions couldn't provide. The crude valve gear wasted steam through poor distribution, but it never failed catastrophically like precision mechanisms did when subjected to dust, debris, and rough handling by minimally trained crews. Most significantly, the welded boiler construction that had generated such controversy proved superior to traditional riveting under extreme service conditions. Military inspection reports documented that riveted boilers developed leaks requiring major shop work at intervals measured in months, while welded units operated for years with minimal attention beyond routine tube cleaning and basic maintenance. The post-war surplus of S160 locomotives created unexpected opportunity for railways worldwide. The U.S. Army offered units for sale at fractions of their construction cost, eager to liquidate war surplus equipment that peacetime military budgets couldn't justify maintaining. Railway administrators in devastated Europe, Asia, and Africa faced reconstruction with limited capital and infrastructure that remained damaged despite immediate post-war repairs. The S160 offered solution that sophisticated European designs couldn't match. These crude wartime engines could operate on tracks still bearing damage from combat operations, tolerate fuel quality that remained inconsistent during post-war recovery, and provide reliable service with minimal maintenance support. Railway systems purchasing surplus S160 units discovered they had acquired unexpected capability that peacetime engineering had never delivered. Poland's state railways purchased 200 units that became primary freight power across the nation's war-damaged rail network. The locomotives operated reliably on tracks that Polish engineers hadn't yet rebuilt to pre-war standards, pulling reconstruction supplies across temporary bridges while consuming whatever coal remained available from mines still recovering from wartime disruption. The unexpected success of S160 locomotives in post-war service transformed international railway operations throughout regions where infrastructure remained primitive or poorly maintained. Railway administrations discovered that the crude American design solved problems that sophisticated European engineering had never addressed successfully. Greece's railway system adopted S160 locomotives for mountain operations where refined European engines had consistently failed. The steep grades and tight curves of Greek mountain railways subjected sophisticated valve gear to frame stresses that disrupted precise timing, causing failures that stranded trains in remote locations requiring expensive recovery operations. S160 units negotiated the same mountain lines with crude reliability. The simple Baker valve gear tolerated frame flexing without catastrophic failure, while short wheelbase navigated curves that longer European locomotives handled only with difficulty. Railway officers reported that American locomotives required minimal maintenance, while European designs demanded constant attention from skilled mechanics that Greece's war-damaged economy couldn't support adequately. Turkey's state railways experienced similar revelation when S160 locomotives proved capable of sustained operations across Anatolia's harsh environment. Summer temperatures exceeding 110 Celsius and winter conditions dropping below zero created thermal extremes that sophisticated European locomotives handled poorly without careful maintenance and high-quality fuel. The crude American design operated through temperature extremes with minimal difficulty. Welded boiler construction tolerated thermal cycling that would crack riveted seams, while simple running gear functioned adequately whether hot or cold. Turkish railway engineers reported that S160 units maintained reliable service using fuel quality that would disable European compounds within weeks. India's railways purchased surplus S160 locomotives for branch line operations, where British-built engines had proven unsatisfactory. The sophisticated compounds that British engineering had developed for Indian service demanded maintenance standards that branch lines couldn't provide, resulting in poor reliability that frustrated operations management. American locomotives operated successfully on neglected branch lines using whatever coal local mines produced. The crude design tolerated fuel variations that would destroy British compounds, while simple construction allowed local workshop personnel to perform repairs using basic equipment. Railway administrators discovered that wartime expediency had created capability that peacetime refinement had missed entirely. The most telling vindication emerged from comparative operational data that railways accumulated over years of post-war service. S160 locomotives operated with availability rates exceeding 90%, meaning they remained in service rather than awaiting repairs, while sophisticated European designs achieved availability barely reaching 70% under similar conditions. The crude American engines consumed more fuel per ton-mile than efficient European compounds, but they ran continuously rather than sitting disabled. Total operational costs favored S160 units despite their inefficiency because repairs remained minimal and parts could be fabricated locally rather than requiring expensive specialized components from distant suppliers. Railway mechanical officers who had initially dismissed S160 locomotives as crude emergency equipment found themselves defending the American design against criticism from engineering purists who insisted that proper maintenance would make European locomotives superior. The operational evidence proved otherwise. Decades of careful European refinement had optimized performance under ideal conditions while creating vulnerability that crude American simplicity avoided entirely. The ultimate vindication of S160 design philosophy emerged through decades of service that extended far beyond anyone's expectations when production began in 1942. Railways that purchased surplus units expecting brief service before replacement with modern power discovered that the crude, wartime engines outlasted sophisticated peacetime designs that should have rendered them obsolete. Yugoslavia's state railways operated S160 locomotives until the 1970s. Long after European engineering had advanced through multiple generations of improved designs, the American engines continued pulling freight trains across Balkan mountain grades where modern diesel struggled with steep climbs and tight curves. Railway engineers who had learned their profession decades after World War II found themselves maintaining equipment their predecessors had dismissed as temporary expedients. The longevity resulted from fundamental design characteristics that wartime urgency had accidentally perfected. Welded boiler construction proved more durable than anyone predicted, with units accumulating millions of miles without developing the leak problems that riveted construction inevitably experienced. The crude valve gear that efficiency experts had criticized as wasteful never failed catastrophically because it lacked the precision mechanisms that sophisticated designs depended upon. Most significantly, the simplified construction made S160 locomotives maintainable by railway workshops with basic equipment and minimally trained personnel. Components could be fabricated locally when replacements wore out, while repairs required only standard machine tools and common welding equipment. Sophisticated European designs demanded specialized facilities and expert craftsmen that many railways couldn't justify economically. The contrast with post-war American locomotive development revealed uncomfortable truths about engineering philosophy. U.S. builders pursued efficiency and performance through increasing complexity that created magnificent machines requiring perfect conditions to operate reliably. The Pennsylvania Railroad's T1 duplex locomotives achieved speeds exceeding 120 mph through sophisticated engineering that made them temperamental and maintenance-intensive. S160 locomotives continued operating in developing nations long after American railroads had abandoned steam power entirely, proving that crude reliability served operating needs better than refined complexity. The wartime engine that American railroads had dismissed as inadequate outlasted every sophisticated peacetime design that replaced it domestically. The final irony emerged as preserved S160 locomotives became valued museum pieces and tourist railway attractions worldwide. Units that had been considered expendable wartime equipment now represented historical significance that sophisticated European designs rarely achieved. The crude American engine that railway experts had mocked in 1942 had become cultural heritage that nations preserved as symbols of resilience and practical engineering. Modern railway historians examining S160 service records discovered that wartime urgency had accidentally created optimal design for worldwide railway conditions. The crude construction that American railroads criticized as beneath their standards proved perfectly suited for railways operating with limited resources and imperfect infrastructure. Military expediency had solved problems that peacetime engineering never recognized as requiring solutions. The S160 story challenged assumptions about engineering excellence that persisted throughout the industry. Railway companies worldwide had pursued sophistication and refinement that optimized performance under ideal conditions while creating vulnerability when conditions deteriorated below perfection. The crude wartime locomotive succeeded because it accepted imperfection as inevitable reality rather than treating it as temporary condition requiring special accommodation. Colonel Hill's philosophy that operational survival mattered more than efficiency had proven correct across decades of worldwide service. The locomotive designed to be thrown away after brief wartime use had become one of the most successful railway machines ever created, not through sophisticated engineering, but through crude simplicity that tolerated real-world conditions better than refined alternatives ever could.